Welcome to Episode 17, California Watershed Management. Northern California catches winter moisture along the upslope of the Sierra Nevada mountains, east of the Central Valley. Large reservoirs at the western base of the mountains even out the availability of this water, because California can experience very dry and very wet winters. This is an application of two-vat flow. Storm moisture received below the snow line goes directly into the reservoir. Up along the Sierra crest, storm moisture waits in a snowpack until the spring melt. The meltwater comes into the reservoir gradually according to a warming weather schedule. Model runs and our performance graphs will be one water year long, starting October 1st and ending September 30th. This is traditional in California, as it keeps the story of the winter delivery and summer use of the same lot of agricultural water together. For this model we have created a generic Northern California watershed system similar to the Shasta, Oroville and Folsom systems. We are generic so we can use our own simplified numbers and operating rules. This is our first model to use automatic control. The one thing we can control is outflow from the reservoir, but our controller will be watching two errors: day-by-day reservoir progress against its standard, and new storm moisture arrival against its standard. Here are the specific numbers we will use. Around 3 million acre-feet arrive in storms and leave in outflows in an average year. This gives an average outflow of 250,000 acre-feet a month. We can dump as much as 1 million acre-feet a month without catastrophic valley flooding during very wet years, or we can limit outflow to 100,000 acre-feet a month when few storms come. 100,000 acre-feet will keep cities alive but limit agriculture. Reservoir capacity is 3 million acre-feet, but we want to stay away from this level, especially early in a year, as outflows over the emergency spillway would be uncontrolled, and a regulation failure. Our outflow control goal is to have 2 million acre-feet in the reservoir September 30th, the end of the water year. This puts us in a good position for whatever comes next. The controller will do whatever it can to achieve this. Some combinations like low current reservoir levels and high new moisture will offset and result in average monthly outflows. This is a big model so we won't go through it block by block, just indicate where the major features are. First our accounts, reservoir, and snow. Then our signal builders, our stored functions to read into the model as we go through each year. Here is a ×1 moisture year and a signal builder. We turn it up or down with a multiplier for wet versus dry years. December through April are usually the big storm months. Here is a signal builder for the spring melt schedule. Each spring month, a certain percent of remaining snow is moved to the reservoir. None is left by late summer. For regulation, we need an average year history of proper reservoir levels. That is in this signal builder. Here is our splitter for storm moisture. 40% becomes lower elevation rain, the rest is snow. The regulations section includes error calculators, and finally a clamping system to keep outflows between 100,000 and 1 million acre-feet. Let's start with our average year graphs. Top graph of the first screen is moisture delivery from Pacific storms in acre-feet per month. It is a rate graph. Since everything is ×1,000 in the model, the peak of this graph is 500,000 acre-feet a month sustained for California's wettest months, with a ramp-up and ramp-down period. Graph 2 is our snowpack wave. Since it is from an account, it is a running total graph. At peak storage, March to April, it holds a bit over 1 million acre-feet for runoff. Graph 3 is back to being a rate graph. It shows a peak snow melt rate of 460,000 acre-feet a month in late spring. Sheet 2 Top graph is a reservoir inflow rate graph, instant rain plus delayed snowmelt. The middle graph is reservoir outflow, and in a normal year is between 200,000 to 400,000 acre-feet per month. The bottom graph is reservoir content in acre-feet. It starts and ends at around 2 million, dips early as November is not so wet, but peaks at around 2.8 million acre-feet during spring runoff. Sheet 3. The top graph and middle graph are moisture and reservoir level error signals, and they won't be very active until we have a non-standard year. The bottom graph is overall error. With no error, it needs to stay near ×1, minimal modification of baseline outflows. Sheet 4 Graph 1 is a running total of delivered moisture from storms. It climbs from 0 to about 2.9 million acre-feet and stays there from the end of the storm season until the end of the graph, September 30th. Graph 2 is the running total of outflows. In a normal year it starts out a bit shallow but then catches up to Graph 1's final level, total in and out usually being equal. The last graph is a debugging signal that can be moved from point to point in the model to get it running. Right now it doesn't signify anything in particular. Now for a 2.5 times normal water year. All the curves are huge. Let's see what our peak reservoir level was. Just about 3 million acre-feet. How about peak outflow? 950,000 acre-feet per month. We avoided major flooding in the Central Valley. Let's see the storm moisture and reservoir level error signals. The storm moisture error is most active through the winter and into spring. The reservoir error takes over the main regulation load during the summer and into fall as necessary. Do we get back down to around 2 million acre-feet by September 30th? Just about. We might get 2 heavy moisture years in a row. How does the system do with a 20% year following an average year? The storm moisture delivery error complains early in the year. The reservoir history error complains all the rest of the year. The output of the regulation system quickly goes to 0, which the clamping system interprets as an order to let only the minimum 100,000 acre-feet out of the reservoir each month. This will keep cities alive, but farming will be cut way back. After a 20% year, we can't get back to 2 million acre-feet in the reservoir by September 30th. 1.4 million acre-feet is the best we can do. Let's enter only 1.4 million into the reservoir account and try a half-normal precipitation year, one dry year after another. Continuing the minimum required monthly outflow, did we make some progress on our year-end reservoir level? We ended at around 1.7 million acre-feet, up from 1.4 million. Half a water year is better than nothing. This is what California has to put up with. See you next time for landing the rocket, another exercise in using a control system. Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voices copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and graphics copyrighted 2019 by William Rhodes Design.